Welcome to the second session of the Physical Sciences, Paper 1. In the previous session, we were looking at the Newton's laws of motion, mechanics in general, where we looked at different approaches to try and tackle the problems that are associated with the Newton's laws of motion. So what we'll be doing in this session, I want us to go further to look at what is called impulse. And that's what this session is all about. And it will help you prep for mostly the third question of your question papers. What we'll do, we'll just go and look at the key aspects of it. The first thing that we'll cover the what impulse is. So what we'll be looking at what is the definition of momentum, and then afterwards we'll move on to look at the change in momentum. Then afterwards, we'll focus on the Newton's second law of motion in terms of momentum. There are two definitions of the Newton's second law of motion. The previous one, remember, it was mentioning that a body will continue in its state of rest until it's acted upon by an external force. So in this case, we will try to define the Newton's second law of motion with respect to the momentum subject. And then fourthly, we're going to look at what impulse is. And then we'll eventually look at the principles of conservation of linear momentum. And then afterwards, we go straight to different types of problems. But specifically, we'll pick up a question from November 2021 to try and address as much as we can the definitions around momentum, the impulse, the Newton's laws of motion, and the principle of conservation of momentum. And then finally, we're going to look at something called elastic and inelastic collisions. We're going to define what elastic collisions are and what inelastic collisions are. The example that I will provide you with is focusing mostly, it can be on elastic or inelastic. And then I will give you a second problem to go and work on in case you happen to have a problem. We'll tackle it in the next session. Right, let's go right into it. I picked a question from May-June 2023. I guess it can be able to address different aspects that we want to cover. Now, what is, maybe let's backtrack a little bit to look at what momentum is. Momentum, we call momentum a product of mass and volume. Each and every object that is in motion contains something called momentum. What is momentum? It is the product that you get when you multiply the mass of an object and the momentum. For example, let's say a body which is 10 kg is moving at a velocity of 2 meters per second. Because the mass is 10 kg and is moving at 2 meters per second, for you to work out the momentum, you take the mass, which is 10, and multiply it by 2, which is the velocity. The 20 kg meters per second are the units that are used to measure momentum. And then the change in momentum, we're talking about, let's say you are applying a force on an object. We say that whenever you apply a force on an object, it's likely to accelerate. What will happen is there will be a change in velocity. So there is a higher chance that when an object is pushed or pulled with a force that is non-zero, F net, that object will change its momentum. So that's where we derive the Newton's second law of motion based on momentum. We say that a body that is that receives a certain amount of force is likely to change the velocity, and that change of velocity creates what is called the change of momentum. So what is Newton's second law in definitions of momentum? Newton's law says that the force is directly proportional to the rate of change of momentum. So in other words, force is the rate of change of momentum. What it means that every time you hear the word rate, it means that time has been put into factor. So if I take a body that is starting with 5 meters per second, let's say it's 10 kg body that starts with 5 meters per second, and as it moves, we apply a force that will accelerate it to 10 meters per second. That change from 5 meters per second to 10 meters per second effectively is causing a change in momentum. Since we say that momentum is a product of mass and velocity, so if you change the mass, if you change the velocity rather, you are likely to change the product's momentum. So, according to Newton's laws of motion, the rate at which it changes, in other words, change in momentum over change in time, is what we define as a force. Right. Then number 2.4, we are looking at the impulse. The impulse is the product of the force, the net force, and the time in which that force is acting on an object. Like in this case, let's say, back to the example that I just shared with you, the body is moving at 5 meters per second, and eventually it starts moving at 10 meters per second. If we are changing from one momentum to the other at a specific time, within a specific time, then we say that the force has been calculated. So an impulse in this case will be a change in momentum, or it can be a rate at which the momentum changes. It can be a product of force and time. Right. So another thing that you need to recall whenever you are working on problems relating to the momentum and impulse is the principle of conservation of linear momentum. The principle of conservation of linear momentum states that in an isolated system, the total momentum is conserved. In other words, if a body has been possessing a certain momentum before, and eventually it changes to another momentum, what will happen in an isolated system? The rate at which the momentum changes, if it's conserved, then we say it's an isolated system. That's why we say the principle of conservation of linear momentum is focusing on the change or that occurs, but it keeps the whole momentum conserved, the total momentum conserved. I'll give an example. Let's say before collision, a body is moving at 20 meters per second, and it is 20 kg as an example. And then after the collision, the body moves at another pace. Right. So what has happened there is that before collision and after collision, still there is going to be a conservation of momentum. Remember, according to the laws of conservation, we are saying that an energy or momentum cannot be changed. It cannot be lost. Right. So part of the velocity would have been adopted by a product that was before the collision. Right. So we're going to look at different types of problems. In this case, we're looking at different types of collisions. There are times when you are looking at two bodies moving in the same direction, and then the one that is behind is moving faster than the one that is ahead. And then they collide. As soon as they collide, a body A that was ahead starts moving faster whilst the body B slows down. That's the first case that is general. And then the other case is where you've got two bodies that are facing each other, and as they face each other, as they collide, sometimes they collide. Case number one, they can collide and bounce back again in the opposite directions. That's case number one. Case number two, sometimes they are heading in the same direction, and then the very moment they collide, they are likely to, one is likely to overcome the other, and they continue in the direction of the one that was moving with a greater momentum. That's case number two. In some cases, it happens that after the collision, they may stop. One can stop and the other one can continue to move. Like, for example, let's say you are playing a pool. When you're playing a pool, what happens is there is ball number one and ball number two, number 8 and number 10. Let's say one is taking a shot. When you take a shot, the very moment you hit the first ball, the second ball is stationary. By the time it bounces, two things are likely to happen. The first ball may reduce its pace or its velocity, or it may change direction. Or sometimes it happens that it stops right where the collision occurred. That's different cases that you are likely to come across when you're working on problems on impulse and momentum. In any case, be it a condition where the bodies change velocity or change momentum, at the end of the day, the principle of conservation of linear momentum says if it's an isolated or a closed system, then it's likely that momentum will be conserved. Right. Then the last part is the elastic and inelastic collision. Remember, every object that is moving at a certain velocity possesses energy. So when we're looking at elastic and inelastic collisions, we are looking at generally energy. So there are two types of mechanical energy. There is kinetic energy and there is also potential energy. Kinetic energy is energy that is possessed by an object in motion. And then whilst potential energy is the energy that is contained in an object that is stationary or that is hanging or that is stagnant, right? So a moving object possesses kinetic energy. Remember, it's moving at a velocity. So the subject of elastic and inelastic collisions is circulating around the subject of energy. If ever a collision occurs between two bodies, let's say they were possessing body A possessed momentum 1 and body B contains momentum 2, what will happen is this. In an elastic collision, before the collision and after the collision, momentum is conserved. In both cases, elastic and inelastic, momentum remains conserved. But there are some times where energy is not conserved. Let's say, for example, two bodies are coming and they collide. Then in some way, somehow, the energy is converted from being kinetic energy into sound energy or light energy or any form of energy. Then what will happen? The energy is not conserved. As much as the momentum is conserved, energy is not conserved. That type of collision, we call it inelastic collision, right? Then the elastic collision, on the other end, then it means that the bodies have energy conserved before collision and after collision. The energy remains the same, and both momentum and energy remain unchanged. In that scenario, we call it elastic collision. All right, let's attempt the problem, maybe just to clarify what I just shared. Right, I picked a question that specifies all of that. Let's go right into it. Right, so in front of you, what you see is two trolleys. Right, two trolleys. One is trolley A and the other is trolley B. According to the statement, it says that trolley A, that has a mass of 7.2 kg, moves to the right at 0.4 meters per second in a straight line on a horizontal floor. It collides with second trolley, which is trolley B, which has a mass of 5.3 kg. After the collision, the trolleys lock together and move to the right as shown in the diagram below. Right. So ignore any frictional effects. In other words, we have got before collision and after collision. Right. Remember the rule. The rule says that there is a principle of conservation of linear momentum. What does it say? It specifies that in a closed system, in a closed or isolated system, the total linear momentum is conserved. Okay? In other words, it remains constant. So to work out a problem like that, let's say the next question says, calculate the magnitude of, number one, the velocity of the trolleys immediately after the collision. How do you work it out? The first thing that you need to understand is that you come up with a conventional direction, or to mention that to the right is positive or to the left is positive. I always recommend that people, they choose to the right being positive so that it's easy to work out. It's not confusing, right? But if you're comfortable with working to the left, it's still fine. But just make sure that you don't lose the track of whether you chose to the right positive or to the left positive. In my case, I'm using the right as positive. All right, so what will happen is this. Before collision and after collision, momentum is conserved. In other words, the total momentum before collision is equal to total momentum after collision. So what does it mean? It means that if I take M1, I will use A, B in this case because A is trolley 1, B is trolley 2. So MA VI1 plus MB VIA should be equal to the final velocities, where we say that M1 or MA V final plus MB V final, right? So you can write it in that format, or you can write it in a format where you combine. Since in this case, after the collision, these two trolleys, they are combined. You can put together mass A plus mass B, and they are moving together with the same final velocity, as you can see on the formula. So what we'll do, we'll proceed and then substitute based on what we have there. You multiply 7.2 kg of trolley A times its velocity. In other words, you work out the momentum for trolley A plus the momentum of trolley B. Since the trolley B was stationary, it means that the momentum for trolley B started off at 0. This should be equal to the momentum of trolley A after collision plus the momentum of trolley B after collision. So in other words, since they are moving coupled together, we then put them together in a bracket format and calculate the final velocity, right? So eventually, if you work out and transpose, collect the like terms, the velocity will be given at 0.23 meters per second. So that's case number 1. It happens sometimes that after the collision, the bodies can be coupled. That's what in physics we call the coupling effect. We normally use the coupling effect to study, like for example, you've got a train and a wagon. Let's say a train, the head of a train wants to connect itself to a wagon. Whenever they come together, there is going to be a collision. And once they come together and move at the same velocity, that's a typical example of this problem. Right? So that's how you generally work on it. The second question says that average net force. I want you to calculate the average work force of the magnitude of calculate the magnitude of the average net force exerted by trolley A on trolley B during the collision. The collision time happened as 0.02. That's what we mean by the contact time. Now, this is where impulse comes in. We say that impulse is the product. There is two definitions of impulse. One, it is the product of the applied force and the time of contact. The second definition says impulse is the change in momentum. So how do we work out the force? We are going to use the formula that specifies that F, or the force of B on A, is given by F net delta T, where we are saying that it's the product of the force and the time. It should be equal to the change in momentum. Do not forget to choose the direction. In this case, conventionally, I chose the right as positive, meaning that the forces that are pointing to the right will be positive. The velocity of the objects going to the right will be positive. Otherwise, it will be negative. Right, so F net delta T is equal to a change in momentum. And then based on that, we can say F net delta T is equal to the mass of the object, final velocity minus initial velocity. Substituting that, we eventually say F net will be equal to 0.0, F net multiplied by 0.02, which is the time it took for them to collide. It will be equal to 7.2, 0.23 minus 0.4. The reason why we chose minus is because you've got final velocity minus the initial velocity. One was moving at an initial velocity of 0.4. So as a result, we end up having F net being negative 61.2 newtons. Right, take note that it's negative. What it means that the force of B on A, check out B. B was stationary, A was moving to the right. So A will exert a force on B that is more to the right. And according to Newton's third law of motion, we specify that if body A exerts a force on body B will exert the same amount of force on body A, but in the opposite direction. So the very moment they came together for 0.02 seconds, within that short space of time, body A exerted a force more to the right, whilst body B exerted a force to body A in the opposite direction. That is to the left. And because it's to the left, no wonder we get the formula or the result being negative 61.2. Right, so be very careful whenever you're reading this question, because sometimes they would ask you a question like the amount of force exerted by B on A, or it can be amount of force exerted by A on B. Right, so you have to read the question very carefully. As much as the forces will be equal in magnitude, direction matters in this case. Right, so no wonder we end up having F net being 61.2 newtons. Right, so I hope this somehow introduces you to the idea of the subject of impulse. Right, so what we'll do in the next session, I want you to be able to go through the November 2022 paper, and then we're also going to go through the November 2021 paper. They are more or less using the similar approach. It's very, very much important for you to understand that. Right. So in the next section, what we'll be looking at more examples that involve the subject of the impulse and momentum. So impulse in general and momentum is used a lot whenever we'll be dealing with the coupling effects or general collisions. Right. So what a takeaway for you in the session will be to say, understand the law of conservation of momentum, understand the subject of inelastic and elastic collision. Understand also the definition of impulse in both scenarios where you are looking at impulse as a product of force and time, and also impulse being the change in momentum. The other definition to remember is the Newton's second law of motion according to momentum. Whenever you are required to define it according to momentum, you need to understand that force is the rate of change of momentum. And every time when we talk about the rate of change of momentum, we are introducing the quantity time. So it's very important for you to understand that when objects are coming together during the time of collision, it's highly likely that there is going to be a force that object A exerts on B. And that force is equal in value, but opposite in direction to the force of A exerts on B. So in other words, the magnitude will be the same, but yet the values will be different. The reason is because of the conventional direction that you will have chosen. If you choose to the right as positive and your overall result is negative, it shows that the force is in the opposite direction on the time of impact. All right. So like we say that sometimes it happens in different cases where object A exerts a force on object B, and on time of collision, they exert that impact, and then they move together coupled, and we call that the coupling effect. Sometimes it happens that they bounce out, and then as they bounce out, in that scenario, we say that it's another term. So what I want you to do is to go and look at different scenarios where the objects collide and apply the principles of momentum. If energy is conserved and momentum is conserved, then we say the object is in an elastic collision. But if momentum is conserved and energy is not conserved, then we say the object is in an inelastic collision. The type of energy we are referring to in this case is kinetic energy. Why? Because an object that is moving possesses the kinetic energy. Right, so in our next session, what we will do, we'll try and identify different scenarios that speak to different examples that we just highlighted. It's been a great lesson. Enjoy the day.